All right, this is video 3 for CS 499 Network Science taught by Dr. Vigil-Hayes. So in the previous video, we talked about using a matrix as a way to start um, discerning whether or not a network belonged to the assortative, neutral, or disassortative network classes. Um, and so we talked about how, just by looking at the direction of the slope or perhaps a lack of slope in the matrix, we might be able to map whether a network was assortative or disassortative or neutral. But let's start putting some more of a quantification on the classification. So one way that we can better quantify assortativity is to look at the degree correlation matrix. So this is the exact same matrix that we were looking at in the previous video. So this is a matrix where we have the degree values ordered from smallest to greatest in the y-axis and in the x-axis. And then we're looking at the probability of finding a node with degrees I and j at the two ends of a randomly selected link. That's kind of what each index in that array is representing. So we have this expression E sub ij, which is representing that degree correlation matrix. And it's important to note that the degree correlation matrix is normalized so that the sum of all probabilities in the matrix is equal to 1. So this should make sense intuitively, right? If we're looking at the probability of any link in a network having nodes with two different degree values, if we were to look at all possible combinations, that should sum to 1. All right. So we also, this was back, I believe, in chapter, probably in chapter 2. We were talking about how the probability of a node with a degree value of k being at the end of any randomly selected link in a network can be described with the expression q sub k. So here we have q sub k is equal to the product of k times the probability of observing k in a network divided by the average degree in the network. So again, this is just going to be the probability if I were to pluck out any random link in a network. This is the probability that at the end of that edge, there is a node with a degree k. That's what this expression means. So we can actually start connecting our degree correlation matrix to this expression q sub k using this summation expression. So here what we're saying is if we were to sum all of the values in a single row in a matrix, it would be equal to q sub I. So that q sub I is representing qk, where k is equal to I. So I is, again, some degree value in the matrix or some column in the matrix. And we're just summing all possible values in the matrix for that I. So this is a way that they are related to each other. So if we were to set ei of j equal to the product q sub I times q sub j. So this is going to be for each index in the matrix, we're going to set it equal to the product of the probability that the node at the end of some randomly selected edge is going to have a degree of I times the probability that the node at some randomly selected edge is going to have a degree of j. That's going to be the value that we're plopping into each index of the matrix. So our random expectation is that For every kind of individual index, we're going to have some value that's equal to this product. And we say that if a network deviates from being neutral, or it deviates from this random expectation, then it's likely that that network is either an assortative network or a disassortative network. So the random expectation gives us an expectation for each index each index value that corresponds to a neutral network. So if all of that seems a little bit non-intuitive or very involved, that's totally okay. There's a different way that we can start examining degree correlations. And one of the ways that we can do that is with this expression here. So let me break this expression down. So instead of using a matrix, we can measure the average degree of each node's neighbors and plot these values as a scatter plot. And so the average degree value of some node i's neighbors is going to be calculated using this knn of ki expression. And here we're just averaging out for every single neighbor that ki has. If there is an actual value of 1, we are multiplying that by the degree value of that neighbor, and then we're just averaging it out by the total number of neighbors. That's really all we're doing with this knn expression. So just imagine if we have, a regular network diagram looking like a graph. You pick a node, you find all of the different neighbors that are connected to that node. You then identify what is the degree of all of those neighbors, and then you're just averaging that out. That's all we're doing with this expression. So what we end up doing is once we have this average neighbor degree value, we can plot that against the degree of a node. So we take some node in the network, we say, okay, what's your degree? We're going to find our x-axis value that corresponds with that degree k, and then we're going to find our average neighbor degree value, knn of k. So that plots our y-axis value, and then we can create a scatter plot. So here in this scatter plot, we have a black line kind of running through the middle. And this black line represents our expectation if we had a perfectly neutral network. So that means that there's absolutely no correlation between a node's degree and the average degree of its neighbors. So in the first example on the right, we have an assortative network. And so here we see a positive linear slope, and note that the x and y axis are both on log scale. So this is a log scale. So when we have a kind of positive slope, that means that we have kind of a positive value exponent that's being used to generate this pattern. If we look into the middle graph, we have a neutral network. And here you can see that the line, if we do a regression, our line is really, really close to being a flat horizontal line that almost lines up with the perfect neutral line. So this is a really good example of what a neutral network looks like when we look at the relationship between the degree and the average degree of a node's neighbors. So finally, on the right-hand side, we have an example of a disassortative network. So here we actually have a negative slope, which again, because we're on a log-log scale, means that we have a negative exponent that's being used to generate this kind of regression line. And we can see that, again, this is exactly what we would expect. As a node's degree gets larger, the average degree of its neighbors gets smaller. So it's exactly what we would expect for a disassortative network. So we can easily classify whether a network is assortative, neutral, or disassortative by examining the degree correlation function. So this is the expression that's kind of used to create a regression through our scatter plot. And it's calculated as KNN equals alpha times K raised to mu. So mu is going to represent the correlation exponent. And this is what we're really interested in because the correlation exponent is actually going to allow us to classify which type of network we're looking at. So if our if our correlation exponent is greater than 0, meaning that it would create on a log-log plot a positive slope, means we have an assortative network. If our mu value is equal to 0, so we have something that looks like a horizontal line on a log-log scale, we have a neutral network. And if we have a disassortative network, our correlation exponent is going to be less than 0, meaning that it would generate a negative slope on a log-log scale. So these are kind of the three major categories. And of course, it's important to note for the neutral network case, it's going to be really difficult to get to exactly mu equals 0. And so usually when we do regressions, there's usually a positive and negative error that we add and subtract to our predicted value for mu. So if we have an error that if we add or subtract it, we get to 0, that's usually good enough for being able to call mu equal to 0. And your book does a really great job going into depth on some examples of this. So to get an idea for the value of the correlation exponent in real networks, let's look at the degree correlation graphs for different real-world networks. So here up on the top we have a power grid, which in a couple videos ago, I explained as being a great example of a neutral network, right? Because it's dependent more on geographic relationship rather than on structural relationships. So nodes don't really form links to each other based on whether or not they have similar degree values, but more because they're actually geographically proximate. And so our mu value here is equal to negative 0.04, which again, if we were to look at the error values, that gets us really, really close to being flat 0. The internet, on the other hand, has a mu value of 0.56. So given that this is so much larger than 0, we would say that the internet is an assortative network. And that's really similar to the networks representing mobile phone calls and scientific collaboration. These are all examples of assortative networks. If we look again at some other networks, so the actor network, we've talked about that, actors working together, that's another example of an assortative network. But then looking at things like email, looking at things like protein or metabolic networks, we start to get this negative slope on a log-log scale, and that's representative of a disassortative network. And maybe this is surprising to you, maybe it's not, but if we were to look at the worldwide network, the web, we would actually find that that's an example of a disassortative network. So good exercise for you to practice and to maybe work on answering in our weekly check-in Slack channel is to think about why it makes sense intuitively that the web would be a disassortative network. What does that mean? What does it mean that hubs don't tend to connect to hubs on the web, or that it's more likely that hubs are likely to be connected to nodes with smaller degrees? So that would be a great question to work out an answer to in our weekly check-in as practice. All right, so in the next few videos, we're going to continue looking at this kind of this phenomena of classifying, and we'll probably do some practices of classifying different networks.